Hello, everyone. It's my great pleasure to welcome you to a new edition of the virtual seminar of geometry with symmetries. And today we have Yi Lai from Stanford University, and she'll be speaking on O2 symmetry of 3D steady gradient Ricci solitons. So thanks, Yi.
Thanks a lot for the invitation and introduction. So today I will talk about the O2 symmetry of 3D static gradient Ricci solitons. And so first, let's talk about Ricci flow. It's a family of Riemannian metrics satisfying a geometric PDE introduced by Hamilton in 1982. And so the equation reads that the derivative of this matrix equals to the negativity of the Ricci curvature. And so we want to see how this Ricci flow does on constant curvature manifolds. And more generally, we want to see how this flows on Einstein manifolds. So Einstein manifolds are Riemannian manifolds satisfying this equation. Ricci equals to lambda times metric, where lambda is a real number. And so we can compute directly to check that if you define a family of matrix GT in the following way. So first, let's see. If GT is -2 times lambda times T dot the metric, and T is between -infinity to 0 if lambda is greater than 0, and then we get we can check that this satisfies the Ricci flow equation. Okay, and can see that this the Ricci flow, the flow is shrinking the metric in this case when lambda is greater than 0, and when lambda is equal to 0, and I'll define the metric just to be the static metric, and T is for all negative and positive times. Okay, and then this is also a Ricci flow in this time, and we'll call it a steady. Okay, and then if lambda is less than 0, and the metric is defined as -2 lambda T dot G T between 0 to infinity. So this is expanding soliton. As T goes larger and larger, this metric becomes larger and larger. So this is expanding. Oh, sorry, not soliton, just expanding flow. Okay, and so the pictures are like the following. So when lambda is greater than 0, the example is that the flow shrinks a round sphere to a singular point as time goes to 0. And if you start the flow from a static torus, then the flow keeps invariant. Okay. And if the metric is negative, the constant is negative, equals to -1, and then the flow will expand this manifold. Okay, so all these flows are self-similar in the sense that modular rescalings, they have isometric time slices. So the time slices are isometric. And this notion of self-similar Ricci flow can be generalized to Ricci solitons. Okay, so Ricci solitons is a generalization to the Einstein manifolds because it satisfies the following equation. So Ricci minus 1/2 the Lie derivative equals to lambda times the metric. Lambda is a real number, and the X is a smooth vector fields. In particular, if X is the gradient of some function f, as is called the gradient soliton. And so in this case, the Lie derivative is 2 times the Hessian of the function f. So the gradient soliton equation is Ricci minus Hessian of F equals to lambda times G. So this is the gradient soliton. Okay, and so based on the intuition we get from these pictures, these three pictures, I'm going to call this Ricci soliton to be shrinking soliton if lambda is greater than 0, and steady soliton if lambda is equal to 0, and expanding soliton if lambda is less than 0. Okay, and today we'll focus on the second case, and the steady soliton satisfies this equation. So focus on the case where we have a steady gradient soliton. And so here lambda equals to 0, so the equation becomes Ricci minus, so Ricci equals to Hessian square of F. Okay, and so we can check easily that this static gradient soliton generate a Ricci flow in the following way. And so consider this family of diffeomorphisms phi t. So these are diffeomorphisms generated by gradient of F, and phi 0 is the identity map. And then we just pull back the metric by this family of diffeomorphisms to get a family of new metrics. Okay, and we can check directly that this is the Ricci flow, satisfies Ricci flow equation, and it is defined for all times. Okay, so this is the Ricci flow associated with a static gradient soliton. And so next, let's look at some examples, in particular in dimension 2 and dimension 3. So the first example of the static gradient soliton is a Hamilton's cigar soliton. Okay, so cigar soliton gets its name because it looks like a cigar. So it looks the following. Okay, so this is a rotation is symmetric defined on R2, and our rotation is symmetric. And the rotational center is the critical point of the potential function F. Okay, so we can check this easily. And there's something more about the cigar soliton we want to say here. So if you choose a sequence of points, pi goes to infinity, so send pi to infinity. And then we look at this, so let's call this cigar to be the manifold AMG, cigar soliton. And then we look at this pointed manifold, pointed at this different pi. Then this will converge to a flat cylinder at infinity. Okay, and so this tells us that cigar soliton is a collapsed solution. Okay, because the flat cylinder has 0 curvature, but the volume is not comparably as large as there. So this is a collapsed solution. And also, we can do something else. If you take a number of a sequence of numbers, lambda I goes to infinity, and we use this number, the sequence of numbers, to blow down this cigar soliton. So we look at this sequence M lambda I inverse G pointed at P. So this time we fix the base point, and we can see that this in the Gromov-Hausdorff sense converges to a ray. Okay, so that's this. So this is called the asymptotic cone of the cigar soliton. It is array. Okay, and the next example is a high-dimensional generalization of the cigar soliton, and it is defined by Bryant. It's called the Bryant soliton. So the Bryant soliton is defined on.
Sorry, when you say array, do you mean including 0, right? The R plus?
Yes, exactly.
It's a half line, so to speak.
Yeah,
okay.
Half line, yes, exactly. Right, so yeah, it's from 0 to infinity. 0 is closed. Yeah. Okay, right. And then for the Bryant soliton, it is defined on Rm, and it is also rotationally symmetric. Okay, but this Bryant soliton, it does not look like a cigar, so it opens up faster than the cigar soliton. So you can have the following picture. Sorry. So it's look like a paraboloid. If you look at the geodesic ball, metric ball at distance r, and then the radius of this ball is roughly the square root of r. Okay, and so I'll be able to using this to show that the scalar curvature, which has the scale of -2, is decays like linearly. Okay, and so here we also want to do something similar as before. And so now we take a sequence of points going to infinity. So pi goes to infinity, and we'll consider the rescaled flow at pi. Okay, so we scale down this metric by the scalar curvature so that the rescaled curvature has normalized the scalar curvature at the base point. And then this will smoothly converges to the three-dimensional cylinder, okay, as I goes to infinity. Okay, and this cylinder is a non-collapsed manifold, implies that the Bryant soliton is also non-collapsed. Okay, and the next I'm going to take sequence numbers to go to infinity and look at its asymptotic cone. Okay, so this time we get the same thing here. So the asymptotic cone is still the array. So that's the asymptotic cone of the Bryant soliton. Okay, and so the next example is a class of examples called the flying wing. Called flying wing. So the flying wing is defined as a 3D static gradient soliton. So here SGS means static gradient soliton. That is asymptotic. So whose asymptotic cone is a sector with angle theta between 0 and pi, strictly between 0 and pi. So such a static gradient soliton is called a flying wing by Hamilton, and also the existence is conjectured by Hamilton. Okay, so and here's our first theorem. So we're able to give a complete affirmative answer to this conjecture. So we find, so this is a combination of working 2020 and 2022. So we'll be able to find for any theta between 0 and pi, we can find a Z2 cross O2 symmetric flying wing whose asymptotic cone angle is theta. Okay, so this is the existence of the flying wing. And so now I owe you a picture of what the flying wing really looks like. And so let me draw a picture of it. Okay, so here is a picture of a 3D flying wing. So there's an edges of the wing, which is so here's a complete geodesic fixed by, so here's a geodesic fixed by the O2 action, and along these edges of the wing, we see that the geometry looks like this. So more precisely, along the edges at the two different ends, the metric looks like R cross cigar. Okay, and here R cross cigar. And in the middle, the geometry looks like R2 cross S1, so the flat cylindrical plane. Okay, and it is asymptotic to the wedge with this angle in this case. Okay, so this is the asymptotic angle, theta. Any question here? Question or comments? Okay. And so now let us take some time to compare our results with some analogous results in mean curvature flow.
So may I ask a question? Sorry, I wasn't fast enough when you asked. Does it have positive curvature?
Sorry?
Does it have positive curvature? Like the Bryant soliton has positive curvature, right?
Yes, exactly. That's
and
a good
same
point.
For the soliton. So does it happen for the flying wings?
Yes. So in fact, we have the result that which shows that all 3D ancient Ricci flow are non-actively curved. And so this is always true for ancient Ricci flow. But if you have static soliton, it always generates an ancient Ricci flow. Yeah. So all of this stuff we talk about today, they are non-actively curved. Yes.
Okay.
Okay. So then next, let us briefly compare these results. It's static soliton to mean curvature flow solitons, although they have different names there. And so, so in mean curvature flow, there's also something called the flying wing. And so that's defined as the following. So that's a convex translating graph. So the translating graph is something that is analogous. The convex translating graph is something that we compare with our Ricci flow static gradient solitons. Okay. And so this is flying wing is defined as this graph defined over a finite slab. So we're defined on this region on R2, where theta is greater than pi. Okay, so what? Let me also draw a picture of this mean curvature flow flying wing. So here's the coordinates of R3, and from 0 to theta. So this, so within this finite slab, in this definition domain, you have a graph over this strip, and so that's a flying wing where it is defined. So it looks like this, a two-dimensional hypersurface. Okay, so if you look at its blowdown of this hypersurface, you can also see that it is asymptotic to an angle between 0 and pi. So that's similar to the Ricci flow flying wing. And there's also a story about the mean curvature flow flying wing. So its first theorem is by Wang Xujia in 2002 and 4, and he first showed that there exists a flying wing in R3. Okay, and then more recently, 2018, just before the pandemic. Okay, and this existence results was generalized to a more complete result. Okay, so it is showed independently by Borney, Lamford, Tinaglia, and around the same time by Hoffman, Eminem, Martin, and White. And so they can show that this existence result is complete in the sense that for any theta greater than pi, they can find a flying wing that is defined on this slab of the width theta. Okay, so now you see that this is let us summarize what we have did so far. So I want to summarize everything in the following diagram and compare these two different objects in this diagram. So in the first column, we have the 3D static gradient soliton on R3. Okay, and then we want to look at their asymptotic cones. And then, sorry. And in the next column, we want to look at the convex translator in R3. So that's mean curvature flow objects and their definition domain. Okay, and so here's first one, we have R cross cigar. So that's a product of the R and the cigar soliton, the two-dimensional cigar soliton. And since the cigar soliton is asymptotic to a ray, and so cross with R, that is asymptotic to a half plane. Okay, so that's a half plane. And we'll have the 3D flying wing, which by definition, its asymptotic cone is a sector with angle 0 to theta. And finally, the 3D Bryant soliton. And that is a degenerated, its asymptotic cone is a ray. Okay, so you can see that the asymptotic cones of the solitons changes continuously from a half plane to a sector, and then eventually degenerates to a ray. Okay, so that's the 3D static gradient soliton. And then for the mean curvature flow translating graphs, there we have the R cross Grim Reaper. So the Grim Reaper is the analog of the cigar soliton. So the Grim Reaper is a curve shortening flow. So that is a picture of the Grim Reaper, a curve, a infinite curve. And so this thing here, its definition domain is R cross 0 to pi, and the mean curvature flow flying wing. And so this is R cross 0 to theta inverse. Our theta is between 0 and pi here. Same here. And then lastly, we have the bow soliton. And it's also similar to the Bryant soliton, which looks like a paraboloid. And this is definition domain is its entire R2. So here we call this soliton to be an entire soliton. Okay, so now that's the comparison we want to make. And so now a natural question to ask is whether we know that this is a complete classification of 3D static gradient Ricci solitons. And to answer this big question, we want to now first look at the last row here. And so I want to see if this, for the last row here, there's a one-to-one correspondence. So first check this, if there is a one-to-one correspondence. And for main curvature flow, now that people already know that this is a complete classification of convex translators, and also the first step is also to show that this is a one-to-one correspondence. Okay, so this is the theorem also by Wang Xujia in 2004. And so he shows he showed that this is indeed a invertible relation between these two. So a convex entire translator in R3 must be the, oh, sorry, I should not say the 3D, that's 2D, sorry. Must be the 2D soliton. Okay, and so now we'll be able to prove the analog of this theorem in Ricci flow. Okay, so what we proved is that a positively curved 3D static gradient soliton asymptotic to a ray must be the Bryant soliton. Okay, so these conditions are compared as following. So this convex is compared to this positively curved condition here. So as we said before, so every static gradient soliton is non-negatively curved, and here we're assuming it is a positively curved just to exclude the possibility. So this excluded that it is a quotient of R cross Agar, which means it's 1 cross Agar. Okay, and the other conditions are compared as this. So the entire assumption is compared with this asymptotic here. Okay, so this is the analog of the theorem in Ricci flow. Any question so far? Okay, so no, let's continue. And so now we have the existence for this unsteady 3D static gradient tree solitons. And so the next thing to consider is to consider their symmetries, and we want to see what symmetry do these solutions satisfy uniformly. Okay, so then and in order to get a good candidate of this symmetry, we want to look at this diagram, this comparison diagram again, but this time let us look at instead of looking at as their asymptotic cones, we look at their symmetries and make a comparison. Okay. Okay, so here we'll look at their symmetry. So now that these compact translators are classified, we know that this the symmetries are clear. So this first one is Z2, sorry, that's Z2. This one Z2 equals Z2 symmetric. And of course, the R cross cigar is Z2 cross O2 symmetric. So the O2 symmetry is the rotational symmetry of the cigar. And then the flying wing, the mean curvature for the flying wing is also Z2 cross Z2 symmetric. And here you have this, the 2D bow soliton is O2 symmetric. And this O2 symmetry can be decomposed as two reflections in the orthogonal direction. So in particular, this O2 symmetry implies Z2 cross Z2 symmetry as well. So that is even stronger than this Z2 cross Z2 symmetry. And for the Bryant soliton, we have O3 symmetry, which also can imply Z2 cross O2 symmetry. Okay, so now with this comparison with the mean curvature flow count translators, we're able to make a conjecture here, so that we believe that this for the flying wing, they should also satisfy the Z2 cross O2 symmetry here. Okay, so now the question is whether we can prove this symmetry for the flying wings. Okay, so now the next theorem gives an affirmative answer to this O2 symmetry. So, okay, so we prove that all 3D flying wings, so 3D flying wings are indeed O2 symmetric. So it means that there is an asymptotic O2 action. Okay. And here's a corollary. Okay, so if now we combine this theorem with this theorem here, so this theorem takes care of the case when theta is equal to 0 and when the asymptotic cone angle theta is 0. Okay, so here takes care of theta equals to 0, and this symmetry theorem takes care of theta greater than 0. And both of cases, so this is Bryant soliton, it is the Bryant soliton, so it must be O2 symmetric. So combined with these two different two theorems, we'll get the following corollary, which says that the O2 symmetry is true for all 3D static gradient solitons. Okay, so that's a statement of the main results. Any questions?
Sorry, yes, do you mean with this table for the Ricci solitons, do you mean this is a complete classification?
Oh, no. So we do not know they are, this is a classification yet.
So the corollary says all known examples are O2 symmetric.
Oh, no. So it says that all static gradient solitons are O2 symmetric. Not only the examples we know, it also includes that maybe there are some examples that we don't know, but they are also O2 symmetric. So this is a general theorem. Does that make sense?
Okay.
So
yeah, but how does it follow immediately? Does it follow immediately from the theorem, or?
Oh, you mean the last corollary?
Yes.
How does it follow from this theorem combined with this one?
Yes.
Is that a question?
Yes.
Okay, sure. Let me see it again. Let's, so for this theorem, it tells us that if theta equals to 0, or theta is the asymptotic cone angle. So if theta equals to 0, then it is a Bryant soliton. So Bryant soliton is O2 symmetric, right?
Yeah.
So that tells us that theta equals to 0 implies O2 symmetric. And this theorem, the second theorem, tells us that when theta greater than 0, which is the flying wing, it is O2, it is also O2 symmetric. Okay, so theta equals 0 and greater than 0. These are the only possibilities for the values of theta. So it covers all the theta values. And so that means these static gradient solitons are O2 symmetric. Because so here that the 3D static gradient solitons can only be these three types. The question that we don't know is that if these flying wings are exactly those that we construct in this theorem. So this theorem, we constructed many flying wings, but it is not known so far. Although we expect that this will be the only flying wing examples. So now the question is now, is this a 1-to-1 correspondence here? Yeah.
Okay.
Sorry, does that answer your question?
Yeah, I think so. So then you prove the O2 symmetry by only using that the asymptotic cone is this
Yes.
sector. You're not
Exactly.
using that it's a flying wing. Okay.
So we define the flying wing just to be without using any symmetry or any other assumption, just to be. So we define as the flying wing just using asymptotic cone angle. So
It's not your flying wing, any potential flying wing. Okay. Okay. I think
yes,
I understood. Yes. Thanks.
yes, yeah. So this might be some confusion here, because so we only define the flying wing using the asymptotic cone angle and anything, nothing else. Yeah, yeah. Thanks for the question. Yeah. Okay. All right, so next let me talk about the proof of the O2 symmetry. And so although here we make a comparison with the O2 symmetry with the Z2 symmetry in the mean curvature flow, but the proof are totally different. So here the Z2 symmetry is discrete, so we can use some maximum principle to get this to get this mean curvature flow Z2 symmetry quite easily. But here the O2 symmetry is somehow continuous symmetry, and so we need to do more work. Okay, so the next part we'll talk about the proof of the O2 symmetry. Only a sketch of the proof, of course. O2 symmetry. Okay, so first we're going to assume that the soliton, the 3D static gradient soliton MG is not the Bryant soliton, because the Bryant soliton has already been understood very well. Okay, so we can assume it's not Bryant soliton. And then step 1. In the first step, we're going to study the asymptotic geometry of this soliton. And in particular, we'll get the following results. So we'll be able to show that it is asymptotic cone angle is theta, which is not equal to 0. So in other words, if it is not a Bryant soliton, we show that it must be a flying wing. Okay, and not only that, we can also get some other estimate. So we can show that the scalar curvature has a positive curvature, has a positive limit at infinity if we go along the right direction. Okay, so here let me first write down this. Okay, so the picture of the soliton is now like this, and so here's a curve gamma. So we can find such a curve gamma so that along these edges, along this curve at infinity, the scalar curvature has a positive equal limit at these two different ends. And after rescaling, we can assume this is equal to 4. Okay. And we also studied the asymptotic geometry of this soliton at infinity. So we can show that for any sequence of points going to infinity, the pointed manifold without any further rescalings will converge smoothly to either R cross cigar, which you can guess that the first situation happens along gamma. If this sequence does not go away from gamma, then the first case happen. Otherwise, if it goes away from gamma, then we can show it converges to R2 cross S1. Okay, so this S1 has radius 1. Okay, so that's something we can show. I can prove in the first step, and then want to then the second step. So so in the second step, we want to do some curvature estimates. So we know that the scalar curvature does not decay along the curve gamma, and in the second step, we'll get even more information than that. So we'll be able to show that the scalar curvature decays very fast in these local, almost flat regions where the geometry is modeled on the flat cylinder, the flat cylindrical plane. Okay, more precisely, what we're going to obtain is the following estimate on the scalar curvature. So it has an exponential lower bound, and it has a upper bound by any polynomial function in the by any degree of the distance to gamma. So so here let's first look at the lower bound of the scalar curvature, and so this constant here 2 times 1 plus epsilon is corresponding to this rescaling this limit here. And so we can compare this with the cigar soliton across R, and so we'll be able to see that compare this lower bound with what we have in R cross cigar, and we'll be able to see that this lower bound is almost sharp. So we can take this epsilon to be arbitrarily small. So the cause is that the constant C epsilon might be really large. So in R cross cigar, we actually know that this epsilon can be chosen as 0. So this lower bound is not optimal, but almost optimal in this case. And this upper bound is true for any integer k. Okay, so there's something we can prove in the for the scalar curvature, and because this manifold is positively curved, so the scalar curvature bound implies a bound on the curvature operator. And in the next step, we want to construct a approximate metric. Okay, so we're going to we're going to find a SO2 symmetric metric. I'll call it G bar. So it approximates the original soliton metric very well, in the sense that the arrow satisfies the following estimate. So 100 norm of the arrow is bounded by its decays also exponentially from the edges gamma. So we'll be able to show something like this. Okay, so it's important for us to be able to get a exponent that is slightly greater than 2. Okay, so later we're going going to combine these two together. All right, so the idea of this step to construct a SO2 symmetric metric which satisfying this decay estimate is that, okay, so if we look at step 1, we know that there are two asymptotic models at infinity, and R crosses R and R2 crosses 1. So these two manifolds are both O2 symmetric. So we'll be able to glue this together to get a approximatic that are O2 symmetric. And then we're going to use some symmetry improvement theorems to improve these approximations away from the edges. And so eventually we'll be able to achieve this exponential decay using the symmetry improvement theorem. Okay, let me see. I think I'll have time to follow this. Okay, so right. So let me give a sketch of this step here. So a sketch of the step 3. So first, as I said, that outside of a compact subset, we do some gluings to get a first approximate metric G bar 0. And so the C100 norm is less than some small constant epsilon. And so this epsilon is holds everywhere. And then we're going to use a symmetry improvement lemma. And I'll be able to deduce that the following is true. So I'll be able to get another approximate metric G1 bar, so that it achieves a better approximation on some even more interior regions. And then I'll do this again, use the symmetry improvement theorem again, see that we can get another approximatic so that this decays even more. But this holds an even more interior region away from gamma. Let's see, 100 times 2. Okay, and so eventually we'll continue this process for k many times. We'll be able to find, so this will be done in an induction process. So in the case step, after case step, we'll be able to find gk bar, which is O2 symmetric, and it achieves this approximation for this region. Okay, and so you see here, so there's an exponential decay away from the gamma of the arrow, and so now we'll just let k to go to infinity, and we take a smooth limit of this approximate matrix. So gk bar converges to g bar, and this limit metric will satisfy the following estimate. So for some small constant delta, that will be able to find this exponential decay of the arrow. Okay, so this is a simple case of getting an approximating metric, and this delta is not good enough. But then later we can improve this delta to 2 plus delta by taking into account the shrinking of distance in the cigar soliton. So this will give us this optimal constant. Okay, so then in the last step, we're going to combine this what I have done before. So step 4. So in the last step, we're going to use this approximate metric to construct a Killing field of the soliton metric. Okay, so first we start by considering the Killing field of the approximate metric. So X is the Killing field of the approximate metric. Okay, so then we're going to evolve X by the following PDE. Laplacian xt. Okay, so basically, this PDE is just the heat equation of the vector fields under Ricci flow, and so at the same time, we consider its Lie derivative of this vector fields under the Ricci flow GT. So GT is the Ricci flow of the soliton, and then this can compute directly that this symmetric to tensor field satisfies evolves by the following equation. So ht is equal to the Leibniz Laplacian, and the initial condition is Lxg. Okay, and so now that you know that Lxg bar, this Lie derivative of g bar is 0, and this will tell you by formula using the last step that this initial condition of h is also very small. Okay, so what we have is that use step 3, we have that h0, the initial condition is less than or equal to this. Okay, and so of course this is much less than if we decrease this exponent to a smaller number, divide delta by 1/2, and so this is and this is the lower bound of scalar curvature. And so this is a consequence of the lower bound of the scalar curvature. So we'll be able to take this delta a bit really small. Okay, and so now the reason that why we want to compare the initial condition of h with the scalar curvature is that somehow we want to use the scalar curvature as a barrier function to control the evolution of the norm of h, and that is because that ht satisfies the following inequality. So we can check that the following is true by using some curvature estimate in dimension 3. We can show that this. So in other words, the norm of h is a sub-solution to this linear PDE, and we also know that under the Ricci flow, the scalar curvature is exactly a solution to this linear PDE. Okay, so this diffusion term, you can rewrite this as the same coefficient as here. Okay, so now this observation will help us to compare h, norm of h at any later times, and the scalar curvature. And so this will imply that by some work, because we know that the scalar curvature under the flow is always a bounded solution, and because the initial condition of h is much smaller than the initial condition of h, and so by some heat kernel estimates, we'll be able to show that the norm of the tensor fields h decays very fast. So this goes to 0 as t goes to infinity. Okay, and now recall that I will define this ht to be the Lie derivative of xt, and so this, after modular the diffeomorphisms, will tell us that the xt modular some diffeomorphisms that will converges to some smooth vector field x infinity, and this x infinity will be the killing field of the soliton metric. Okay, so x infinity is the killing field, and so now I'll find the killing field to the soliton metric, and here's some subtlety here. So we can also show. So we don't want that this killing field is 0. So we can also exclude this. So we can also show that X infinity is not a trivial killing field. Okay, and then it generates an isometry. And then we can show that this isometry is an O2 isometry. Okay, so this will complete the proof of the O2 symmetry theorem. Okay, so that's what I want to talk about today. Thanks very much for your attention.
Many thanks for an excellent talk. Are there any questions, comments? I do have a few questions. I was letting other people speak first, but here in these computations, everything is with respect to the Ricci flow metrics, right? So the moving.
Yes.
There's no background metrics. The Ricci flow that you're computing, say the Laplacian H is okay.
Right. That's yes.
And when you say, I mean, you use this comparison, it looks a bit dangerous because your manifold is non-compact, right? So there's no maximum principle to apply for free.
Exactly. Yes. So that's why we want to avoid using any maximum principles, but instead we'll look at the
heat kernel.
heat kernel. Yes. So we're
Right.
going to look at the. So let me just sketch this here. So we want to look at the heat kernel of this equation. So let's call the heat kernel as this. And then we'll be able to first show that for any fixed y, that this heat kernel fixed is 0 at time 0, and this heat kernel converges to 0 as t goes to infinity. Okay, and then I'll be able to split this. Okay, so now because H is a subsolution to this, and so I'm going to show, and so this there's a comparison principle is used here. So this is less than the heat kernel involuted with the initial data. And so now I'm going to split this integral into two parts. So on the briefly speaking, on the compact part, this goes to 0 by this fact, because this heat kernel itself goes to 0. And on the non-compact part, we're going to use the scalar curvature as a comparison function. So because this is less than the scalar curvature times an arbitrarily small number, so just replace this by sorry. So replace this by epsilon times the scalar curvature. And then the integral of this guy here is less than or equal to epsilon times a constant, because the scalar curvature remains bounded. And now you have this constant going to 0. And so the non-compact part of this integral is also going to 0. And so this will give you this decay of H. Does it make a little sense?
Yes, excellent. Yes, of course. Very nice. So may I ask a second question? Or third maybe. So are you, I mean, I know that these are collapse solution, the flying wings, right? So they won't show up as, say, blow-ups of finite time singularities, but are you aware of any, say, ancient solution on S3 that arises, you know, from minus infinity from a flying wing? Does it make sense?
Does the do you mean that if there's oh right, so let's first talk about the collapsing part. Yeah, so if you consider about the compact Ricci flow solution, then yes, so these flying wings are not singularity models for the compact Ricci
Right.
flows. But if you think about a sequence of collapsing Ricci flows, then these flying wings will be potential singularity models for this kind of limit. Right, so
Right.
because you don't have no non-local collapsings here for a sequence of collapsing Ricci flows. Right.
Okay.
As
That's
for
a
the
good point.
second question, are you asking that if we can find a 3D ancient flow on S3? Is that the
Are you
question?
aware of it? Yes, yes. You know, sometimes because scalar curvature is bounded backwards in time by the Hanach inequality or whatever, so you can take a limit without rescaling, and you expect to see a steady soliton, right?
Yeah, that's right. That's
So it's natural. I mean, there are examples, I guess, which have cigar cross R as steady soliton, or maybe something flat, right? But are you aware of a flying wing appearing? That would be
yeah.
very
So
interesting.
I think no one has constructed this kind of examples yet on S3, but I do believe they exist. So like
Mhm.
for example, I think at first you can at least you can construct a pancake solution, which is this kind of solution. Looks like this pancake. So this is defined on S3, but so here, if you take a backward limit at some fixed point, then this will converge to R cross sigma.
Right.
So basically, you will get a lot of let's say R cross cigars on the boundary of this ancient pancake here. Okay, and I think you can also perturb this a little bit. So that's something that I really believe you can construct. And and then if this in this case, then it is also I think it's also possible to construct some solution like where you can identify a flying wing.
I see.
Yeah, so yeah, you know what I mean. So
Yeah,
here,
from the picture, it looks very, very possible.
yeah,
Mm.
yeah. Well, this yeah, I think it might be possible to construct these solutions by gluing up this two different flying wings together. So by doing some glue ups, you got this compact region, and then you run a Ricci flow and shift the time backwards, and you hope that you will get a ancient solution by taking a limit of these flows, and that will look like yeah. There are some subtleties. Yeah, of course.
All right, excellent. Further questions for the speaker? Well, if it's not the case, let's thank her again for a beautiful talk.
Thanks.